Good afternoon, folks. How are you today? We are in week 11. So, in weeks 11 and 12, we are going to do our last lab number 6, on Germany and quench test. So, here is the big picture. We are going to study isothermal transformations in eutectoid steel. Then we will see what microstructures we get when we continuously cool that eutectoid steel. And we'll learn about hardenability, another property of steels. Then we are going to conduct Germany and quench test on two steels, a plain carbon steel and a medium alloyed steel. And on those, we have done Rockwell hardness testing. So you're going to measure the diameter of those Rockwell indents using Fiji and draw hardenability curves for the two steels. So let's see. In lab number 5, you learned about annealed steel. So in annealed steels, what we do is we cool very, very slowly. So when we take a eutectoid steel, at high temperature it is austenite, and when we slowly cool it, essentially we keep the specimen in our furnace and turn off the furnace, and then it slowly cools through. We have 100% perlite. This perlite is a two-phase microstructure composed of ferrite mostly, which is the light phase, the white color phase. It is 88%. And then these dark lines are cementite, which is 12% only. Cementite is very, very hard. Ferrite is very, very soft. So what we have is we have dispersion of these hard layers in a soft matrix, if you like. So that provides strengthening. So now in this particular case, we had cooled very, very slowly. Now what happens, suppose if we cool it very fast to different temperatures and hold it there? So when we say isothermal transformations, iso means constant, and thermal, of course, is temperature. So we are looking at constant temperature transformations. So what we are doing is when we cool through this eutectoid reaction, previously we cooled very slowly. Now what we are going to do is we have got austenite here, single phase, and we are going to cool it very fast and hold it at different temperatures. So we'll hold it at a temperature very near the eutectoid temperature, maybe cool it very fast and hold it at another intermediate temperature, and then maybe very, very low temperature. So what we will find is that our phase diagram says we should have two phases, alpha and Fe3C. So we'll find out that austenite transforms to perlite, which is composed of these two phases. And you have already seen perlite structure. If we cooled it to an intermediate temperature and held it there, austenite will become something called bainite, which is also the same two phases, but they have a different structure. The cementite in this is kind of a needle shape instead of a layer shape. And then finally, if we quench it to a very low temperature and hold it there, we will form martensite, which is a one-phase structure. So what we do is we construct these isothermal transformation diagram. So in eutectoid steel, These isothermal transformation diagrams are also called TTT diagrams, where it is stands for temperature, time, and transformation. So previously, when we slowly cooled it, time didn't play a role. Now time plays a role. So we plot. So this is temperature, and this is time at a given temperature. So obviously, this is our eutectoid temperature, 723 degrees C. Above it, we have all austenite. So what we do is think of it as if we have a C-shaped curve. So we start with austenite and we cool it below eutectoid temperature and we hold it there. So what happens is nothing happens up to a certain period of time, and then perlite begins to form. So here perlite begins to appear, and then imagine we have another C curve like this, which we'll call perlite finish curve, and from this to this time, austenite will transform completely, and after that we'll just have perlite, all perlite. So it takes some time for austenite to begin transforming, and then it takes some time for the transformation to be complete, and we have 100% perlite. So this nose, we call it temperature of the nose. So if we quench it to a temperature in between eutectoid and this nose temperature, we will form perlite. What if we cool it to a temperature below? In this case, again, same thing. We hold it there, nothing happens, austenite remains austenite, and then we have this bainite start curve. So austenite begins to transform into bainite. And then when we hold it there, bainite transformation is complete. And after that, the steel is all 100% bainite. So let's see these transformations. These are diffusion-based transformations. And again, you can see that we can even differentiate between different kinds of perlite. So if the temperature is high, we'll get coarse perlite. If temperature is low, we'll get fine perlite. Same thing here. Upper bainite is like coarse bainite. Lower bainite is like fine bainite. So here is coarse versus fine perlite. So you can see here the interlamellar spacing is large compared to here, where interlamellar spacing is so small that we cannot differentiate between white and dark layers. Here is a comparison of mechanical properties. So here we do slow cooling. We'll talk about continuous cooling, but we are just looking at properties of coarse perlite. Here, fast cooling, or think of it as low temperature isothermal transformation, fine perlite. So you can see here, for any given percent carbon, yield strength, coarse perlite, is smaller than that of fine perlite. Tensile strength, smaller than that of fine perlite. But elongation is larger. So when interlamellar spacing is decreased, we go from coarse to fine perlite, strength increases and ductility decreases. So this is a principle we have learned uh, many times in previous labs. Here is how bainite looks like. So instead of alternate layers, here cementite started growing and kind of petered out. So cementite starts growing, peters out, so it forms these needle kind of shapes. So this is our coarse or upper bainite, and this is our fine or lower bainite. Here is a comparison of perlite in bainite. So you can see here is our transformation temperature. At high transformation temperature, we form perlite. At low transformation temperatures, we form bainite. Here is the nose temperature. So you can see because our dispersion is finer in bainite, it would have a higher strength. And higher strength means smaller elongation. So you can see as we go to the right, tensile strength decreases, but elongation increases. Now there is something funny happening at about nose because there's a mixture. And whenever there's a mixture, we don't see the same kind of trend. And then again, you will see as perlite becomes coarser and coarser, strength decreases. So the key idea here is at high temperature, we form perlite because at high temperature, diffusion rates are higher. So we form that layered structure. At lower temperature, we form bainite. At lower temperature, diffusion rates are lower. So these cementite plates cannot grow to be large layers. But in any case, both of these are diffusion dependent transformations. That's why temperature and time play a big role. Our third transformation is called Martensite transformation. So what happens is eventually we get to a very low temperature called Martensite start temperature, and correspondingly there is a Martensite finish temperature. So if we start cooling it, if we cool austenite below Martensite start temperature, some of the austenite becomes Martensite. If we cool it below Martensite finish temperature, all of the austenite becomes Martensite. So austenite to Martensite transformation is first of all diffusionless. So it is instantaneous. Time does not play a role. Only temperature plays a role. So it is temperature dependent, not time dependent. Whereas in diffusion was both time and temperature dependent. And the reason we say it is temperature dependent is notice as we cool down, we have 100% austenite, then it becomes transforms. Let's say it becomes 50% here, Martensite, and then below MF will be 100% Martensite. So the temperature is what tells us how much of austenite has transformed. So what happens is that at high temperature, the austenite was FCC. When we cool it down, it wants to become ferrite, BCC, but it has got all this carbon there. So if we cool it very fast, it wants to become BCC with all this carbon trapped in there. It deforms, it becomes tetragonal. And this is what the Martensite structure is. So Martensite is a single phase, it is body-centered tetragonal. Here is what the microstructure looks like. The black stuff is Martensite, the white stuff is austenite, which has not transformed. So again, want to emphasize high temperature austenite is FCC, face-centered cubic. If we cool it slowly, it transforms to ferrite and carbon diffuses out. If we cool it very fast, the carbon doesn't have time to diffuse out. So instead of becoming BCC, it becomes body-centered tetragonal. So what is body-centered tetragonal? The two edges are equal to A, which is 2.8 nanometers, and the third edge is different size, C, which is different from A. In this case, C is greater than A. So let's see what happens. Here is structure of martensite showing carbon and iron and how it deforms from FCC to BCC structure. I'm not going to go in detail, but here, let's look. As we increase the percent carbon, the size of A decreases, whereas size of C increases. There is more and more distortion. So what happens to mechanical properties? As we have more and more carbon in our martensite, it'll have more and more hardness. Eventually, we cannot strain harden that BCC crystal anymore. So after a while, increasing more carbon doesn't give any benefit. So usually most medium carbon steels have no more than 0.6% carbon or so. Okay, so we have three kind of structures we can form isothermally. At high temperatures, we get perlite. At medium temperatures, we get bainite. And at very low temperatures, we get martensite. And in terms of hardness and strength, as we go down this reaction scheme, hardness and strength, of course, increases, but ductility goes down. Ductility and toughness go down. Okay. So here is the entire TTT diagram. So again, for eutectoid steel, perlite star curve, top half of the C, red curve, perlite finish curve, bainite start curve, bottom half of the C, bainite finish curve, martensite start temperature, and martensite finish temperature. Remember, amount of martensite depends on temperature to which we quench. So if we quench to say somewhere here, we get only 50% martensite and other 50% austenite remains untransformed. So that is called retained austenite, and that really ruins the properties of steels. So in 50s and 60s, when we were trying to understand transformations in steel, it was very important to measure that retained austenite. Now that we know so much about steels, we know how to prevent having retained austenite. Okay, so what happens, suppose instead of quenching and holding at a temperature, we do continuous cooling. That means temperature keeps dropping as time goes along. So in that case, what happens is this C curve shifts slightly down and to the right. So let's look at continuous cooling transformation diagrams. So these are called CCT diagrams as opposed to TTT diagrams. So again, temperature, and now this is just time. And as I said, the C curves have shifted down and slightly to the right, and we need only the top half of the C, you will see. And then, of course, we have martensite start temperature and martensite finish temperature. Okay, so let's see why we need only top half of the C. So let's suppose we have austenite at this temperature and we are cooling. Then there are two critical cooling rates. One is this critical cooling rate. So this is critical cooling rate left. If we cool any faster than this rate, we will always form martensite. So anything faster than this rate, only martensite. Let's suppose we cool, the next critical cooling rate is like that. We say cooling rate, notice because temperature is dropping with time. So this we'll call critical cooling rate, right? If we cool any slower than this cooling rate, we will always hit perlite start and perlite finish. So we will get all perlite. In between, we'll get martensite and perlite mixture. Okay. So notice these cooling rate never hit the bottoms half of the C curve. So we cannot form bainite in continuous cooling in eutectoid steels. So as I said, if you have a fast cooling rate, faster than this red one, we get all martensite. If we have very slow cooling rate, slower than this blue curve, we get all perlite. In between cooling rates, we get a mixture. Of course, martensite is very hard, perlite is relatively soft, mixture would be in between medium hard. And again, I want to emphasize that in continuous cooling, bainite cannot form in eutectoid steel.